All right, so we looked at how light is a wave, and we've calculated wavelength and frequency based upon the speed of light. But now we're going to take a look at how light is a particle. The learning goals for this would be that you could define a quanta or quantum of energy and explain how light is a particle and calculate the energy of photons. So whenever scientists were experimenting, they were finding that light could not only be a wave, that there needed to be other properties. And they saw this in whenever they were heating up objects, they only emitted certain frequencies of light whenever they were at a given temperature. And so the scientist that looked at this was Max Planck, and he was searching for an explanation of why light was being emitted by heated objects and how that worked. Einstein also was showing the duality of light, that it was both a particle and a wave. When we look at Planck's study, so if you watch the video that I have linked for this, I think that's really helpful. It shows how Planck came about the conclusion that energy was released in what's called a quanta. And so matter can gain or lose energy in small specific amounts called a quanta. The quantum is the minimum amount gained or lost, and this is really the basis for what will be then quantum mechanics. What you can think of this like is looking at a ramp, which would not be an example of a quanta, versus a staircase. And so Planck said that there were definite energies and there was a minimum amount. So in order for there to be a certain amount of energy that was released, it had to be a certain minimum amount for that to happen. The other experiment that looked at and showed the particle nature of light was something called the photoelectric effect. I also have this video linked on Blackboard for you, but this is where the electrons are emitted from a metal surface when a light of a certain frequency shines on it. So what does that mean? What we're looking at here is that certain wavelengths of light are going to be able to cause an electron to be emitted, but lower or different wavelengths of light are going to not allow that to happen. So it would be larger wavelengths of light might not allow that to happen. With the photoelectric effect, if you watch the video, it shows how this works. But there's a charged rod, which is positive. It causes the metal plate to become negative, and then the gold foil leaves, which are down here, become positive, and so they separate from one another and are held apart. If you shine a light onto the metal plate, if it's a low frequency, so it's a long wavelength, just a light from a regular light bulb, it's not going to be enough to discharge that plate, meaning to make it less negative. So as it would make it less negative, then that would mean that the gold foil leaves would come together. So a regular light's not going to be able to do that. However, if UV light is used, then it will start to cause the electrons to be removed just because of the frequency of that light. And so what scientists looked at was that for the photoelectric effect, light would also have to be a particle that's carrying energy, that's allowing then that energy to be transferred to the electron so that the electron can be released. Whenever UV light is used, what we see is that the gold foil leaves come together, which indicates that the metal plate is becoming less charged or electrons are being removed from it. This packet of light energy is what we call a photon. So it's a particle of light, and it is what's going to carry the energy of light. So we talked about how wavelength and frequency are inversely related. Whenever we look at wavelength and energy, they are also inversely related, which means that frequency and energy are directly related. So the more or the higher the frequency, then the more energy that the light particle has. Whenever we look at photons of light, if we look at red versus blue, a photon of red light, which has a longer wavelength, is going to carry less energy than a photon of blue light will. We look at this with the magnetic spectrum, the electromagnetic spectrum, and how energy and frequency are inversely related to wavelength. And so radio waves will have low energy, and gamma rays will have high energy. Here's just some examples of what the different rays and different parts of the electromagnetic spectrum are used for. So gamma rays would be produced by stars, These are going to be high energy. We talked about with radiation how these would be more damaging. X-rays for medical use, and you can read through the rest of those. So let's just check for some understanding. So see if you can arrange visible light, X-rays, and microwaves in order of increasing wavelength, increasing frequency, and increasing energy per photon. So if you need to pause the video for a minute to do that, go ahead and do so. So if you went over the answers, here are the answers. So with wavelength, the longer it is, the less energy it has. And so in order of increasing wavelength, meaning it gets bigger, X-rays would be the shorter wavelength and microwave would be the longer. With frequency, shorter wavelength will be higher frequency, and so for both frequency and energy, it will be in the opposite direction. So you'll have microwave is the smallest, then higher frequency and energy would be visible light, and then the highest energy and frequency would be X-rays. So let's go ahead and order visible light, green, red, and blue, and then order it the same thing in order of increasing wavelength, frequency, and energy per photon. Take a minute to answer these questions. If you need to pause the video, go ahead and do so. So here are your answers here in order of increasing. So blue would be the shortest wavelength, then green, then red. And then for frequency and energy, they would be in the opposite direction since they are inversely related. So one more practice concept question. Yellow has a longer wavelength than violet light. Therefore, yellow light has more energy per photon than violet light. Yellow light has less energy per photon than violet light. Or both yellow light and violet light have the same energy per photon. So go ahead and answer this question. Pause the video if you need to at this time. So for this one, the answer that we would have is yellow light has less energy per photon than violet light. This is because it has a longer wavelength than violet light. So we're going to do a few practice problems. This is looking at calculating light energy using Planck's constant. So Planck, again, was responsible for identifying a quanta of energy, which we look at as a photon, which is a packet of light energy. So the equation to calculate the energy of a photon is going to be E equals hv, or E equals Planck's constant times the frequency of the light. So let's do a few practice problems together. All right, so again, we're going to do some practice problems. Our equation is going to be E equals hv, which is going to be the energy of the photon is equal to the Planck's constant and the frequency of light. So Planck's constant is going to be 6.626 times 10 to the negative 34th joules times seconds. All right, so what is the energy of a photon from the violet portion, so violet light, if it has a frequency of 7.230 times 10 to the 14th second per second, or hertz? So our frequency is going to be 7.230 times 10 to the 14th second to the negative 1, which would also be hertz. Okay, so we'll just plug that into our equation. E equals hv, so 6.626 times 10 to the negative 34th joules times seconds, 7.230 times 10 to the 14th seconds to the negative 1. So our seconds will go ahead and cancel out. And we're left with joules. So if we do the problem and the math for this, we would get 4.791 times 10 to the negative 19th joules. And that would be the energy of our photon of light. All right, so if we do another problem, so we're going to say that the green line of the atomic spectrum has a wavelength of 535 nanometers. Calculate the energy of a photon of light. So remember that we had our other equation, which was going to be that the speed of light is equal to our wavelength times our frequency. And then we have energy is equal to Planck's constant times our frequency. So in this case, we're going to have to do two steps to solve for our problem. What I will also do is this. So you can either solve each equation separately, or you can solve our variables and then plug them in together. So if I rearrange our speed of light equation, then I can say that my frequency is equal to the speed of light divided by the wavelength. So then I can plug that into my energy equation, and my energy equation is equal to Planck's constant times the speed of light divided by the wavelength. So we know Planck's constant, which is h, so 6.626 times 10 to the negative 34th joules times seconds. In this case, we have our speed of light as well, so 3.00 times 10 to the 8th meters per second. And then we have our wavelength, which was given to us in 535 nanometers. So we're going to have to go ahead and convert that to meters. So we're going to say that 10 to the 9th nanometers is equal to 1 meter. And so our wavelength would be 5.35 times 10 to the negative 7th meters. Whenever we plug these in to solve, so we would have energy is equal to Planck's constant, or h, 6.626 times 10 to the negative 34th joules times second. Multiply that by the speed of light. And then divide that by our wavelength, 5.35 times 10 to the negative 7th meters. So as we look at this, what we should find is that we're going to have our seconds cancel out, our meters cancel out, so we're only left with joules, which is our unit of energy. We should have 3.72 times 10 to the negative 19th joules. If you have any questions, please don't hesitate to ask. We will do more practice problems in class.